A hidden architecture shapes our entire cosmos. This is the magnetic skeleton of the universe, a vast and invisible framework of force that guides the birth of stars and the fate of galaxies. By the end of this journey, you will understand how this cosmic scaffold might be actively restraining the universe's most violent energies. We will uncover what these magnetic fields are holding back from us and explore the profound mysteries they conceal about the very nature of reality. What invisible force most captivates your imagination? This cosmic scaffold is woven from the fabric of space itself. It is the magnetic skeleton, a vast and interconnected network of invisible lines of force. These fields stretch across unimaginable distances, threading through entire galaxies, binding clusters of galaxies together, and even filling the immense, empty voids between them. Picture the universe not as a collection of isolated islands, but as a single, living entity with a nervous system made of magnetism. This framework is incredibly faint, a ghostly presence compared to the magnet on your refrigerator, yet its influence is everywhere. It guides the slow, cosmic dance of gas clouds, shepherding them into the nurseries where stars are born. Without this subtle direction, these clouds might never collapse under their own gravity to ignite new suns. It shapes the evolution of the largest structures we know, acting as a cosmic architect that determines where matter flows and how galaxies grow. This invisible skeleton is the universe's hidden choreographer, silently directing the ballet of creation on the grandest stage imaginable. Our journey to uncover this magnetic skeleton began not in the depths of space, but right here in our own solar system. Centuries ago, astronomers peering through early telescopes noticed something peculiar about our sun. Dark blemishes, which we now call sunspots, seemed to dance across its fiery surface. It was in these temporary stains that scientists first detected the undeniable fingerprint of a magnetic field, a force powerful enough to suppress the sun's seething heat and create these cooler, darker patches. This was the first concrete proof that magnetism was not confined to our planet. It was a cosmic phenomenon. The search then expanded to our home galaxy, the Milky Way. How could anyone detect a force field stretching between the stars? The answer came from starlight itself. As light travels through the vast clouds of dust that drift through interstellar space, its waves can become polarized, all vibrating in a single preferred direction. This subtle alignment is a direct result of the dust grains being spun into order by the Milky Way's own gentle magnetic field. We were essentially reading the galaxy's magnetic signature in the very light that reached our telescopes. Another crucial clue came from a ghostly, shimmering glow that seemed to emanate from the galaxy itself. This is synchrotron radiation, a specific kind of light produced when electrons, whipped to nearly the speed of light, spiral along the lines of a magnetic field. We were no longer just seeing the effects of magnetism on dust. We were witnessing the magnetic field in action, accelerating particles and making the galaxy itself glow with an invisible hand. Today, our vision has expanded across the cosmos. We now have the technology to detect these faint magnetic signatures not just in our own galaxy, but in galaxies millions, even billions of light years away. We see their fields twisting through colossal spiral arms. Most astonishingly, we have found immense magnetic fields woven throughout the vast clusters that bind thousands of galaxies together, and even in the seemingly empty deserts of space between these clusters. This skeleton is not a local feature. It is a fundamental, universal fabric, and its discovery forces a profound question upon us. What cosmic event, what fundamental law of physics, could have woven this magnetic tapestry across the entirety of existence from the very beginning? Detecting a force you cannot see requires reading the universe's subtle signatures. One of our most powerful tools comes from the light of quasars, the intensely bright cores of distant galaxies. As this light journeys for billions of years to reach us, It travels through the vast, magnetized webs of gas and dark matter that connect the cosmos. The magnetic fields in these cosmic filaments leave a distinct imprint on the light, polarizing it in a specific way. By analyzing the polarized light from thousands of these celestial beacons, we can trace the magnetic fields they pass through, using them like distant lighthouse beams illuminating an invisible fog. Another crucial technique relies on a phenomenon called Faraday rotation. Imagine a radio wave traveling through space, its polarization orientation fixed like a compass needle. When that wave passes through a region with a magnetic field and a thin soup of electrons, something remarkable happens. The magnetic field gently twists the orientation of that polarization, rotating it. The amount of this twist tells us the strength of the magnetic field and the density of the material it is moving through. It is as if the universe itself is sending us a coded message in the spin of light, and we have learned to decipher it. To collect these faint signals, we use some of the most sensitive instruments ever built. Radio telescopes like the Very Large Array, with its 27 dish antennas working in concert, and sprawling networks like LOFAR, which uses thousands of small antennas across Europe, act as our cosmic ears. They listen patiently to the whispers of the universe, gathering the polarized radio waves and the subtle Faraday rotations. Supercomputers then process this immense flood of data, weaving it together to create the first all-sky maps of the cosmic magnetic skeleton. These are not pictures of stars or galaxies, but charts of invisible force, revealing the grand architecture that has been there all along. We are finally drawing a map of the unmappable, and what this map reveals is a structure so vast and powerful it challenges everything we thought we knew about cosmic evolution. This grand magnetic map reveals a structure far more intricate than anyone anticipated. The cosmos is not randomly sprinkled with galaxies, but organized into an immense and beautiful architecture known as the cosmic web. Picture a colossal spiderweb spun on a scale of billions of light years, with glowing galaxies clustered at the intersections of its silken threads. These are the filaments, the highways and byways of the universe, composed primarily of mysterious dark matter and traced by a sparse hot gas. And woven directly through the heart of these cosmic threads are the magnetic fields we have been searching for. They are not passive residents. As the universe evolved, gravity pulled matter into these vast filaments, and in that process, the primordial magnetic fields were stretched, amplified, and woven into the very fabric of the web. Think of it like pulling on a tangled ball of magnetic string, the strands aligning and strengthening as the structure forms. This intergalactic gas, the raw material for future galaxies, does not flow freely. It is channeled, guided by these magnetic threads like water directed through an invisible aqueduct system. The fields act as a subtle director, influencing where the gas ultimately pools and, by extension, where new galaxies can be born and grow. This magnetic skeleton is not just a relic, it is an active participant in the construction of the universe, shaping its evolution from the shadows. But this discovery only deepens the central mystery. Where did these foundational magnetic fields come from in the first place? What cosmic event in the earliest moments of time could have planted these seeds of force that would one day grow to guide the formation of everything we see? Deep within the heart of a galaxy cluster, magnetic fields reveal their true power. These clusters are the universe's great cities, containing thousands of galaxies all bound together by gravity. But the space between those galaxies is not empty. It is filled with a superheated, thin gas known as the intracluster medium, and this entire ocean of searing plasma is magnetized. We can see the evidence of this in two spectacular phenomena: radio halos and radio relics. A radio halo is a vast, diffuse cloud of radio emission that envelops the entire center of a cluster. This glow is synchrotron radiation, the telltale light of electrons spiraling at near light speed along magnetic field lines. It paints a picture of a turbulent, magnetized core. Radio relics, on the other hand, are different. They are often found on the outskirts of clusters and are thought to be colossal shock waves, the aftermath of cosmic collisions where clusters merge. These shocks act like natural particle accelerators, revving up electrons and amplifying the magnetic fields to incredible intensities, creating giant, arc-like structures of radiolight that can stretch for millions of light years. The strength of these fields is staggering. While a typical refrigerator magnet might have a strength of 100 Gauss, the magnetic fields within a galaxy cluster, though diffuse, can reach intensities of several microgauss. That might sound faint, but when spread across a volume of space that could contain thousands of galaxies, the total energy is almost beyond comprehension. This immense magnetic force exerts a profound influence on its environment. One of its most critical roles is to act as a cosmic insulator. The intracluster gas is incredibly hot, over 10 million degrees, and heat naturally wants to flow from hot regions to cooler ones. But the tangled web of magnetic field lines acts as a barrier, suppressing the conduction of heat. This prevents the cluster's core from cooling down too rapidly, which in turn regulates the flow of gas onto the central galaxies. Without this magnetic blanket, gas would cool and flood into the central galaxy at an uncontrollable rate, likely leading to ferocious bursts of star formation that would burn out quickly. The magnetic field, therefore, acts as a governor, a subtle yet powerful force that modulates the growth and evolution of every galaxy within the cluster's domain. It is the unseen hand that maintains balance in these cosmic metropolises, but such immense power must be holding something else in check. What happens when this magnetic restraint is broken? This magnetic blanket, so vast and powerful, must have a beginning. Its origin story is one of the greatest puzzles in modern cosmology, pushing our understanding back to the very first moments of the universe. The leading theory takes us to an almost incomprehensible epoch known as cosmic inflation. In the first fraction of a second after the Big Bang, the universe is thought to have undergone a period of hyper-fast expansion, stretching from a subatomic speck to a colossal size. This violent stretching would have created ripples in the very fabric of space-time, and within that quantum turmoil, the first feeble magnetic fields could have been born. These would have been the primordial seeds, infinitesimally weak fluctuations woven directly into the expanding cosmos. Another possibility lies in the subsequent phase transitions. As the hot, young universe cooled, it may have undergone sudden shifts in its fundamental state, much like steam condensing into water. These cosmic rearrangements could have released immense energy, creating turbulent motions in the primordial plasma that, in turn, generated the first magnetic fields. These theories suggest the skeleton was part of the universe's blueprint, imprinted at its birth. But there is a compelling alternative, a more gradual origin story. This is the cosmic battery effect. It proposes that the very first magnetic fields were not primordial at all, but were instead generated by the large-scale motions of the early universe. How does this work? Imagine a vast spinning cloud of ionized gas in the early cosmos. Because electrons are lighter than atomic nuclei, they respond more quickly to the cloud's rotation. This creates a tiny separation of charge, a slight current, which, according to the laws of electromagnetism, generates a weak magnetic field. This is the seed. From this incredibly humble beginning, a powerful process takes over, the galactic dynamo. As galaxies form and rotate, their swirling motions of conductive gas can amplify these tiny seed fields, stretching and twisting them, transferring the immense rotational energy of the galaxy into magnetic energy. Over billions of years, a field weaker than that of a common magnet can be amplified into the vast, structured force we observe today. So, did our magnetic skeleton arrive fully formed in the universe's first instant, or was it built slowly, piece by piece, through the patient work of cosmic engines? The answer remains hidden, and with it, a deeper secret. If these fields were indeed present from the very beginning, their influence would have been far more profound than just shaping galaxies. They may have been the universe's first line of defense, holding back something unimaginable from the moment of creation itself. This process of amplification is a cosmic engine of immense power, and its fuel is chaos. Deep within the swirling heart of every galaxy, and in the turbulent plasma between them, a relentless cycle is at work. This is the turbulent dynamo, a natural engine that transforms the raw energy of motion into magnetic force. The key ingredient is that the plasma, the superheated gas stripped of its electrons, is an excellent conductor of electricity. Any movement within this conductive fluid can, in theory, create and amplify a magnetic field. But how does a weak, disorganized field become a coherent, powerful force? The dynamo accomplishes this through three fundamental actions: stretching, twisting, and folding. Imagine a weak magnetic field line as a faint strand of elastic thread floating in this moving plasma. As the gas swirls in vast, turbulent eddies, it stretches the field line, pulling it taut. This single action alone amplifies the field's strength. Then comes the twist, the rotation of the galaxy, or the complex vortices within a cluster of galaxies don't just stretch the field, they also twist it into complex loops and helices. Finally, the chaotic motion folds the stretched and twisted field back onto itself, stacking lines of force together and compounding their power. This cycle is not a gentle process. It is a continuous, turbulent storm of motion that repeatedly stretches, twists, and folds the magnetic field. With each turn of this chaotic cycle, the magnetic energy grows exponentially. A seed field trillions of times weaker than the Earth's magnetic field can, over hundreds of millions of years, be amplified into the microgauss strength fields that weave through entire galaxy clusters. This is not a gentle building of power, but a runaway reaction fed by cosmic motion. The entire galaxy acts as a colossal, self-sustaining generator. Its rotational energy, drawn from the gravitational collapse that formed it in the first place, is systematically converted into magnetic energy. This process is so efficient that it naturally leads to a profound question. If this dynamo can create such immense magnetic forces, what prevents it from running away completely and consuming all the energy of a galaxy? There must be a natural limit, a point where the magnetic field grows strong enough to fight back against the very turbulence that created it. This balance between creation and resistance is the silent regulation that allows the magnetic skeleton to exist without tearing the cosmos apart. A delicate equilibrium that has shaped the universe we see today. This delicate balance of magnetic forces does more than just shape galaxies. It also builds an invisible prison for the universe's most energetic particles. The magnetic skeleton acts as a cosmic cage, trapping and confining high-energy cosmic rays. These are not rays of light, but atomic nuclei, mostly protons, that have been accelerated to nearly the speed of light. They are the fastest, most energetic bits of matter in existence, and without the magnetic fields, they would simply fly off into the void in straight lines. But they carry an electric charge, and that makes them subject to the invisible hand of magnetism. As a cosmic ray enters a region of tangled magnetic field lines, its path is no longer straight. It begins to spiral tightly around the magnetic field lines, corkscrewing its way forward. When it encounters a kink or a twist in the field, it is reflected back, bouncing from one magnetic mirror to another in a chaotic, zigzagging path. A particle that could cross a galaxy in 100,000 years if traveling freely might instead be trapped for millions of years, bouncing around endlessly within the magnetic maze of the galactic disk. This confinement has a profound effect on the entire energy budget of the universe. By trapping these particles, the magnetic fields dramatically increase their density and their residence time within galaxies and galaxy clusters. The energy stored in this swirling sea of trapped cosmic rays becomes immense, contributing pressure that can support giant gas clouds against collapse or even help drive colossal winds blowing out of galaxies. The magnetic skeleton, therefore, is not a passive scaffold. It is a dynamic containment system that governs the flow of the universe's most violent radiation. It keeps this incredible energy reservoir bottled up, influencing how galaxies evolve and how matter is recycled across cosmic time. But what if this cage were to fail? What happens when a cosmic ray does finally break free from its magnetic prison? The same magnetic pressure that builds cosmic structure also applies a gentle universal break. This invisible force does more than guide gas clouds, it actively resists their collapse. Within the dark, cold nurseries known as giant molecular clouds, where new stars are born, the magnetic skeleton reveals its role as a cosmic regulator. Gravity wants to pull every particle inward to crush the cloud into a dense, hot core that will ignite as a star. But the magnetic field, woven through the cloud like a web of elastic bands, pushes back. It provides a form of pressure support, a stiffening within the cloud's very heart that counteracts the relentless pull of gravity. Think of it like trying to compress a balloon filled with both air and a tangle of resilient springs. You can squeeze, but the internal pressure fights you every step of the way. This magnetic resistance means that only the densest, most massive pockets of gas, where gravity's grip is overwhelming, can overcome this support and collapse to form stars. The process is slowed, stretched out over millions of years, turning a potential firestorm of star birth into a more measured and orderly procession. This subtle regulation has a profound impact on the life of a galaxy. A galaxy where magnetic fields are weak might experience furious, explosive bursts of star formation, burning through its cosmic fuel in a relatively short time and leaving behind a population of aging stars. But a galaxy with a strong magnetic skeleton is granted a different fate. The rate of star birth is moderated, its fuel reservoir conserved. This allows for a long, stable evolution, giving life a chance to emerge around its more stable stars. The magnetic fields are not stopping creation, they are pacing it. They are the reason the universe is not a fleeting fireworks display of frantic stellar activity, but a long, slow-burning story. By holding back the raw power of gravity, this cosmic skeleton has shaped the very rhythm of cosmic evolution, ensuring that galaxies have the time they need to grow old gracefully. This magnetic regulation extends far beyond the quiet nurseries of star formation to the most violent events a galaxy can produce. When a massive star dies in a supernova explosion, or when matter spirals into a supermassive black hole at the galaxy's core, it unleashes enough energy to blast vast amounts of gas clear out of the galaxy itself. These are galactic winds, hurricanes of plasma that can rage for thousands of light years. Left unchecked, such a wind would scour a galaxy clean of its star-forming fuel in a relatively short cosmic time, effectively starving it and halting its growth. But the magnetic skeleton intervenes. As these titanic outflows surge outward, they do not travel through empty space. They must push through the galaxy's pervasive magnetic field, a web of force that is already entangled with the very gas the wind is trying to expel. Instead of allowing a clean, rapid escape, the magnetic fields act like a complex system of reins on a wild stallion. They channel the outflow, forcing it to follow the pre-existing lines of magnetic force. This channeling does two critical things. First, it drastically reduces the wind's efficiency. A significant portion of the wind's kinetic energy, its raw power of motion, is diverted into further twisting and amplifying the magnetic fields themselves. The wind ends up fighting the very structure that contains it, losing momentum with every light year it travels. Second, and more profoundly, this magnetic guidance prevents a large fraction of the heavy elements forged in stellar explosions from ever leaving the galaxy. These elements, everything from the oxygen we breathe to the iron in our blood, are launched into the wind. If the wind escapes freely, it carries these precious materials out into the barren intergalactic void where they are lost forever. But when the magnetic fields suppress the wind, they force much of this enriched gas to fountain back down, recycling it into the galactic disk to be incorporated into the next generation of stars and planets. This magnetic containment is why galaxies can self-regulate. It prevents them from blowing themselves apart in a fit of youthful rage, allowing for a long, sustainable evolution. The very elements that make life possible were held back from a cosmic exodus by this invisible magnetic hand. This subtle regulation of cosmic ingredients brings us to a profound and haunting possibility. Could the magnetic skeleton be more than just a cosmic architect? Could it be a silent gatekeeper for life itself? The universe is unimaginably vast and ancient, filled with countless stars and likely billions of planets. Yet we see no signs of other civilizations. This is the core of the Fermi paradox, the great silence that contradicts the high probability of alien life. The answer might not lie with the aliens, but with the invisible framework that shaped their worlds. By pacing the birth of stars, the magnetic fields directly control the production and distribution of the elements essential for life. A universe without this magnetic break would be a chaotic and violent place. Stars would form in frantic, short-lived bursts, rapidly forging heavy elements in their cores and then scattering them in supernova explosions. But without the magnetic confinement that suppresses galactic winds, these newly minted elements, the carbon, oxygen, and iron, would be violently blown out into the empty intergalactic void, lost forever. The raw materials for planets and people would be dispersed into a cosmic desert, never coalescing into stable, rocky worlds. Furthermore, a galaxy experiencing such rapid, unregulated star formation would be a dangerous neighborhood. The frequency of nearby supernova would skyrocket, bathing planetary systems in lethal doses of radiation, sterilizing any fledgling life before it could gain a foothold. The magnetic skeleton, by imposing order on this chaos, creates the conditions for longevity and stability. It ensures that star formation is a slow, sustained process, allowing for the gradual enrichment of galactic gas with heavy elements. It keeps those precious materials close, recycling them within the galactic disk so they can be incorporated into new generations of stars and planets. This slow, patient rhythm gives life the time it needs to emerge and evolve on stable, long-lived worlds orbiting calm stars. So the great silence we observe might not be because life is rare, but because the specific conditions that allow it to persist are rare. The magnetic skeleton, by holding back the universe's inherent violence and wastefulness, may have carved out the quiet, stable corners where beings can eventually look up and wonder at the stars. It poses a staggering thought. Are we here not in spite of the cosmos, but because of its hidden magnetic foundations? But this invisible hand may be shaping more than just the world of light and matter we can see. The magnetic skeleton might also be interacting with the universe's greatest mystery, dark matter. This enigmatic substance, which makes up over 85% of all matter in the cosmos, has so far revealed itself only through its gravitational pull. It does not emit, absorb, or reflect light, which is why we call it dark. Yet some physicists are now asking a daring question. Could certain types of hypothetical dark matter particles possess a tiny, fundamental magnetic property? This idea, while highly speculative, opens a fascinating door. If such a particle existed, it would not be completely blind to the cosmic magnetic fields. It might experience a subtle force, a weak interaction that could nudge it ever so slightly as it moves through the magnetized fabric of space. This interaction would be incredibly faint, a whisper against the roar of gravity, but over billions of years, even a whisper can have a profound effect. The influence might work in the opposite direction as well. We know dark matter forms vast, spherical halos around galaxies, providing the gravitational scaffolding upon which the visible galaxy is built. The powerful magnetic fields generated by that galaxy's dynamo, swirling through its disk and reaching out into its halo, could potentially exert a force on these magnetically sensitive dark matter particles. This could subtly alter the dark matter's distribution, making its halo slightly more compressed or structured than our gravity-only models predict. We have not detected this yet, but it offers a potential clue. The observed shapes of dark matter halos mapped through gravitational lensing sometimes show features that are difficult to explain with gravity alone. Could the invisible magnetic skeleton be leaving its fingerprints on the invisible dark matter, creating a subtle imprint we are only just learning to look for? This is the frontier of cosmology, where the two greatest unknowns of the universe, its magnetic framework and its dark essence, might be secretly intertwined. If they are, then the skeleton's role is even more fundamental than we dreamed. It would not only be holding back cosmic rays and regulating star birth, but also shepherding the invisible 90% of reality itself. This grand magnetic web we have been exploring, this cosmic skeleton of force, is built upon a fundamental asymmetry. Every magnet you have ever held, from a simple compass needle to the one on your refrigerator, has two poles, a north and a south. They are an inseparable pair, a cosmic couple that cannot be divorced. Break a magnet in half, and you do not get an isolated north and an isolated south. You simply get two smaller magnets, each with its own north and south pole. This is one of the most basic rules of electromagnetism, a rule our entire magnetic universe seems to obey without exception. Yet this very rule presents one of the deepest theoretical puzzles in all of physics. Our most ambitious theories, the ones that attempt to unify all the fundamental forces of nature into a single, elegant framework, make a startling prediction. In the unimaginable energy of the first moments after the Big Bang, something else should have been created, not just paired poles but isolated ones. These hypothetical particles are known as magnetic monopoles. A magnetic monopole would be a particle that is pure north magnetic pole or pure south, a solitary point of magnetic charge wandering the cosmos. According to the math, these objects should be incredibly massive, potentially stable, and should have been produced in vast quantities in the universe's fiery birth. They should be everywhere, and yet, despite decades of searching with the most sensitive detectors ever built, not a single confirmed magnetic monopole has ever been found. Their absence is a glaring hole in our understanding, a cosmic crime with no body. So where did they all go? The structure of the cosmic magnetic field itself might be holding the key to this mystery. One compelling idea is that the very same cosmic inflation that may have planted the seeds for the magnetic skeleton also diluted the monopoles into oblivion. Think of it this way: if the early universe was a dense, hot soup filled with monopoles, the period of hyper-fast inflation would have stretched space-time itself to an incredible degree. The monopoles, once crowded together, would have been pulled impossibly far apart, their density plummeting to virtually zero. The observable universe would then contain so few of them that finding one would be like searching for a single, specific grain of sand on all the beaches of Earth. The magnetic fields we see today could be the lasting echo of an era that effectively erased its own monopole problem. Another, even more fascinating possibility is that the monopoles are not missing, but are hidden, trapped and confined by the very magnetic fields they helped to create. In the complex phase transitions of the early universe, as the fundamental forces separated from one another, vast, tangled structures of magnetic field lines could have formed, much like cosmic strings or domain walls. Monopoles could have become bound to these structures, with their magnetic field lines snagged and caught in this primordial spaghetti of energy. They would be there but imprisoned, unable to move freely through the cosmos. We would not be able to detect one passing by because they are not passing by. They are frozen in place, woven into the fabric of space-time itself. The cosmic magnetic skeleton, then, might be more than a scaffold. It could be a cosmic prison, holding back not just energy and matter, but the very evidence that would complete our most profound theories. The silent, pervasive magnetic fields that guide the birth of stars and the growth of galaxies may also be the universe's way of keeping its deepest secrets under lock and key. What other fundamental truths might be concealed within this invisible architecture, waiting for us to learn how to see them? This magnetic cage, for all its power, has a critical weakness. Deep within the turbulent heart of solar flares and the violent borders of Earth's own magnetic field, a dramatic process unfolds, one where the cage itself breaks open. This is magnetic reconnection, a fundamental and explosive rearrangement of the cosmic skeleton. The principle is simple in theory. When two regions of magnetic field with opposite polarity are pushed together, their lines of force can suddenly break. They do not simply bounce off each other. Instead, they cross-connect, snapping into a new, lower-energy configuration, like two stretched rubber bands suddenly swapping ends. In that instantaneous reconnection, all the pent-up magnetic energy that was stored in the stretched field is released in a violent burst. This energy doesn't just vanish. It is dumped directly into the surrounding plasma, superheating it to millions of degrees and violently accelerating charged particles to nearly the speed of light. We see this happening on the Sun, where reconnection events trigger solar flares and coronal mass ejections that can hurl billions of tons of plasma across the solar system. We measure it at Earth, where reconnection on the night side of our magnetosphere funnels solar wind energy into our atmosphere, creating the brilliant curtains of the aurora. Yet for decades, this phenomenon has presented a glaring mystery. Classical physics, which describes how charged particles should move in a plasma, predicts that magnetic reconnection should be a slow, gradual process. The magnetic fields in a plasma are, in a sense, glued to the material, and this ought to create a tremendous resistance, a bottleneck that would prevent the fields from breaking and reconnecting quickly. The math says a large-scale reconnection event in the solar corona should take days or weeks to unfold, but observations show it happens in a matter of minutes or even seconds. The energy is released orders of magnitude faster than the textbooks say it should be. This is not a minor discrepancy. It is a fundamental failure of our models to describe the behavior of the universe's magnetic skeleton in its most dynamic moments. The skeleton, it seems, has a way of breaking itself that we do not fully comprehend. Solving this puzzle means looking into the chaotic world of plasma itself. The leading theory points to phenomena that classical models ignore, effects that become dominant only at tiny scales. As the magnetic field lines are pressed together, they form an incredibly thin current sheet, a narrow layer where electric currents are intensely focused. Within this layer, the particles may stop behaving as a smooth, continuous fluid and begin to act as individual particles. Their own kinetic motions, their tiny inertial effects, could create instabilities that break the magnetic glue, opening up a bottleneck and allowing reconnection to proceed at a ferocious pace. It is as if a dam, expected to leak slowly, suddenly develops a complex network of cracks that cause it to shatter all at once. This rapid reconnection is not just a curiosity. It is the primary mechanism by which the magnetic skeleton unleashes the energy it has been holding back. It is the universe's pressure relief valve, a built-in system for converting stored magnetic energy into heat, light, and violent motion. Every time a star unleashes a flare or the aurora dances in our polar skies, we are witnessing this mysterious, rapid reconnection at work. The skeleton is not a rigid, unchanging prison. It is a dynamic, living structure that can tear itself apart in an instant, releasing powers that shape the environments of planets and stars. Understanding why it breaks so easily is the key to understanding how the cosmos manages its own immense energy. This hidden architecture holds an energy of staggering proportions. To grasp its true scale, we must move beyond the faintness of individual fields and consider their collective might. Picture the magnetic energy woven through a single galaxy cluster, a volume of space so vast it could contain thousands of galaxies. The total magnetic energy stored there, when summed across every cubic light-year, can surpass the entire energy output of all the stars within that cluster for millions of years. This is not a minor component, it is a dominant player. How does this hidden reservoir compare to the universe's other great energies? Consider cosmic rays, those ultra-fast particles trapped by the magnetic cage. The energy density of these raging particles is significant, often rivaling that of starlight itself. Yet, in many regions of space, the energy stored in the confining magnetic fields is comparable to, or even greater than, the energy of the particles they imprison. The cage itself can be as massive as the beast it contains. Then there is the energy of motion, the turbulent churning of interstellar and intergalactic gas. This turbulence is the fuel for the dynamo, the raw chaos that builds the magnetic fields. Remarkably, as the dynamo reaches its peak, the energy in the magnetic field can approach a significant fraction of the energy in the turbulent motions that created it. The two enter a state of rough equilibrium, a tense standoff where the field is strong enough to resist being torn apart by the chaos, but not so strong that it can suppress the turbulence entirely. This balance is what gives the magnetic skeleton its stable, enduring form. But the most humbling comparison is with gravity, the force that sculpts the cosmic web. On the very largest scales, the energy bound up in gravitational fields, the potential energy of the universe's entire mass distribution, is still the ultimate ruler. It is the gravity that builds the clusters and filaments, creating the stage upon which magnetism acts. Yet, within that stage, the magnetic energy is far from negligible. In the spaces between galaxies, within the clusters and the vast voids, the magnetic field energy can be the dominant form of energy aside from gravity itself. It is not the lead actor, but it is the most powerful supporting character, shaping the scenes that gravity has set. This redefines our understanding of cosmic dynamics. We often think of the universe in terms of gravity and light, but we have been overlooking a massive, invisible energy bank. This reservoir does not just sit idly, it actively participates. When magnetic reconnection occurs, it is this stored energy that is violently converted into heat and particle acceleration. When the fields suppress galactic winds, they are leveraging this energy to exert pressure and guide flows. The cosmic energy budget has a major line item we can't directly see, one that has been quietly influencing the balance of power for billions of years. What cosmic events could tap into this vast reservoir, and what happens when this hidden energy is finally unleashed? Unlocking the secrets of this magnetic architecture requires us to build a universe inside a machine. Scientists are now using some of the world's most powerful supercomputers to simulate the birth and evolution of the cosmic magnetic skeleton. This is a monumental challenge, one that involves solving the complex equations of magnetohydrodynamics, or MDH. Think of MDH as the rulebook that governs how a magnetized fluid behaves. It is the mathematical fusion of the laws of magnetism with the laws of fluid motion, describing how a conductive plasma swirls and how that swirling motion in turn twists and amplifies the magnetic fields embedded within it. To simulate a single galaxy, let alone the entire cosmic web, these computers must track billions of individual particles or cells of fluid, calculating the gravitational forces, the fluid pressures, and the intricate push and pull of magnetic fields on a mind-boggling scale. Every single interaction influences the whole, creating a cosmic dance of unimaginable complexity that must be calculated one tiny time step at a time. The goal is to rewind the tape of cosmic history. These simulations often begin with the faintest possible seed fields, the kind theorized to exist just after the Big Bang. They then set the universe in motion, letting gravity pull matter into filaments and halos, and watching as the turbulent dynamo awakens within this growing structure. We can witness in accelerated time how the primordial magnetic fields are stretched and woven into the great cosmic web. we see how they are amplified within collapsing gas clouds and how they begin to channel the flow of intergalactic material. These virtual universes allow us to run experiments we could never perform in reality. What happens if we turn the magnetic fields off entirely? The simulations show a starkly different cosmos. Without magnetic pressure to support them, giant gas clouds collapse far more readily, leading to a frenzied early burst of star formation that quickly burns out. Galactic winds, unimpeded by magnetic confinement, blast away most of the heavy elements, leaving galaxies starved and sterile. The universe without its magnetic skeleton is a chaotic and short-lived place, lacking the long-term stability we observe. By comparing these simulations with our actual maps of the magnetic sky, we can test our theories of its origin. Do the simulated fields match the observed strength and structure of the fields in galaxy clusters? Do they produce the same large-scale patterns we see in the polarized light from distant quasars? Each new, more detailed simulation brings us closer to answering the fundamental question of whether this skeleton was part of the universe's original blueprint or a structure that built itself over eons. These digital universes are our testing grounds, allowing us to witness the invisible forces that have silently shaped our cosmic home from the very beginning. These faint whispers from the cosmic web are now being captured in stunning clarity by a revolutionary ear on the Earth. The low-frequency array, or LOFAR, is not a single giant dish but a sprawling network of thousands of simple antenna stations scattered across Europe. By combining their signals, this telescope acts as a single instrument with a collecting area that would be physically impossible to build any other way. Its specialty is listening to the long, low-frequency radio waves that are the signature of the universe's most ancient and diffuse magnetic phenomena. This is the realm where the cosmic skeleton's faintest filaments become visible. LOFAR deep observations are producing the first high-fidelity maps of magnetic fields stretching through the vast emptiness between galaxy clusters. We are no longer just inferring their presence, we are starting to see their intricate structure directly. The data reveals that these intergalactic fields are not just simple strands. They are turbulent and complex, showing patterns of amplification and structure that existing theories struggle to explain. The sheer extent of these fields is what is so challenging. They are found in regions of space so empty and pristine that there has not been enough time, according to some models, for galactic dynamos to have seeded them. The magnetic fields appear to be a fundamental part of the cosmic web itself, woven into its fabric from the very beginning. This points compellingly towards a primordial origin, suggesting these magnetic seeds were planted in the universe's first moments and were then stretched to cosmic scales by the expansion of the universe itself. LOFAR is showing us that the skeleton is not just an accessory to the cosmic web, it is one of its essential components. Every new map from this powerful instrument forces us to redraw our models of cosmic evolution, pushing us closer to understanding the true, ancient source of the force that shapes our reality. But the whispers LOFAR hears are only the beginning. A far more powerful ear is now under construction, one designed to listen to the universe's magnetic symphony with a clarity we have never before possessed. This is the Square Kilometre Array, or the SKA, a project of such staggering ambition it will redefine radio astronomy. When complete, its thousands of antenna stations will be spread across 2 continents, South Africa and Australia, forming a single telescope with a total collecting area of, as the name implies, 1 square kilometre. This colossal scale grants it a sensitivity that is almost beyond comprehension, allowing it to detect the faintest magnetic signatures from the farthest reaches of space and time. The SKA will not just see the magnetic skeleton, it will map its every filament and node in exquisite detail. It will trace the magnetic fields within the earliest galaxies, revealing how they were first woven into existence. It will produce 3-dimensional charts of magnetism throughout the cosmic web, showing us precisely how these fields channel the flow of intergalactic gas and influence the growth of the largest structures in the universe. This revolutionary power comes from its ability to perform surveys of the sky with both incredible speed and phenomenal resolution. Where current telescopes might take years to map a single patch of sky, the SKA could do it in days, covering the entire heavens with a precision we can barely imagine today. It will measure the Faraday rotation from millions of distant quasars and galaxies simultaneously, building a dynamic and living map of the magnetic universe. This is the key to unlocking the origin mystery. By seeing the magnetic fields in the very first galaxies and in the pristine voids between them, the SKA's data will provide the ultimate test for our theories. Will the patterns we see match the predictions of the primordial inflation model, showing fields that were stretched to cosmic scales at the dawn of time? Or will they reveal a more complex history, one where the cosmic battery effect and dynamos built the skeleton piece by piece over billions of years? The telescope's unparalleled view will allow us to witness magnetic reconnection events as they happen in distant galaxy clusters, finally providing the data needed to solve the mystery of why this process occurs so violently and fast. The SKA will peer into the heart of the cosmic cage, showing us exactly how it traps particles and releases energy. It might even detect the subtle, telltale imprints of magnetic fields on the distribution of dark matter, offering our first glimpse into a possible connection between the universe's visible force and its invisible mass. This is not merely another telescope, it is a time machine for force, a device that will trace the history of magnetism from the present day all the way back to the cosmic dawn. The silent questions we have been asking for decades are about to meet a machine built to answer them, revealing the full story of the power that has been holding back the cosmos. Peering back to the universe's infancy means reading its most faded and ancient writing. The light from the first stars and quasars has traveled for over 13 billion years to reach us, and woven into that faint signal could be the signature of the earliest magnetic fields. As this primordial light passed through the magnetized gas of the young cosmos, its polarization would have been subtly twisted by the Faraday effect, the same phenomenon we use nearby. Detecting that tiny rotation in such an incredibly old and faint signal is like trying to measure the spin of a single photon after an unimaginably long journey. It pushes our telescopes to their absolute limits, requiring us to stare at the same patch of sky for hundreds of hours, gathering every precious bit of light. Even then, the signal is buried under noise from our own galaxy's magnetic field and the atmosphere itself, a whisper nearly drowned out by a roaring crowd. To find the universe's first magnetic whisper, we must learn to separate it from every other magnetic voice in the cosmos. This forces us to look for an even older, more fundamental imprint, one left on the universe's very first light. Just 400,000 years after the Big Bang, the cosmos cooled enough for atoms to form, releasing a flash of radiation that still fills all of space today. This is the cosmic microwave background, the afterglow of creation itself. If magnetic fields were present in that primordial plasma, they would have left their mark on this radiation in two key ways. First, the fields would have exerted a pressure on the electrons in the plasma, creating tiny, swirling motions. These vortices would have imparted a distinct curl-like pattern to the polarization of the CMB light, a specific signature known as B-mode polarization. Second, the simple presence of a magnetic field in the early universe would have slightly altered the way sound waves traveled through the primordial soup, changing the very statistics of the temperature variations we see in the CMB sky. We are searching for these ghostly patterns with increasingly sophisticated instruments like the Simons Observatory and future space missions. Finding them would be a direct glimpse into a magnetized universe before the first star ever flickered into existence. It would prove that the cosmic skeleton is not a later addition but was part of the universe's foundational blueprint. Yet so far, the evidence remains elusive. The signals we predict are incredibly faint, and they can be mimicked by other effects, like the gravitational lensing of the CMB light by all the matter it has passed through on its long journey to us. Disentangling the primordial magnetic imprint from these later distortions is one of the greatest challenges in modern cosmology. We are sifting through the static of 13 billion years, searching for the faint, ordered pattern that would reveal the invisible hand that was already at work, shaping everything to come from the very first moments. These ultra-high-energy cosmic rays are the universe's most powerful natural particles. Each one carries the kinetic energy of a professionally thrown baseball, all compressed into a single, microscopic proton or atomic nucleus. They are the fastest, most energetic bits of matter known to exist, and their origin is one of the most enduring puzzles in astrophysics. The fundamental challenge in tracing them back to their violent births lies in the very magnetic skeleton we have been exploring. Unlike light, which travels in a straight line, these charged particles do not follow a clear path from their source to our detectors. As soon as an ultra-high-energy cosmic ray leaves its home, it enters the vast, magnetized web of the intergalactic medium. It immediately begins to spiral around the invisible lines of magnetic force that thread through the cosmic voids and filaments. Its journey to Earth is not a straight shot, but a chaotic, zigzagging random walk, a drunken stumble through a labyrinth of invisible walls. A particle that might have traveled from a distant galaxy in a few tens of millions of years, if it moved in a straight line, can instead be delayed and deflected for hundreds of millions of years, its original direction completely scrambled by the time it finally reaches us. This magnetic scattering is so extreme that when one of these rare particles strikes our atmosphere, creating a shower of secondary particles, we look back along its incoming trajectory and see only a blank patch of sky. The source is completely obscured. It is as if we are trying to find a single lighthouse by studying the path of a single wave that has bounced off 1,000 rocky shores along the way. The magnetic skeleton acts as a cosmic hall of mirrors, perfectly disguising the locations of the universe's most powerful particle accelerators. To solve this mystery, we cannot just look for the particles, we must first understand the maze itself. By using our growing maps of the extragalactic magnetic field, we can start to run simulations tracing potential particle paths backwards. We take the arrival direction of an ultra-high-energy cosmic ray, and using a model of the magnetic web, we calculate all the possible paths it could have taken to get here. This doesn't give us a single point of origin, but rather a vast, smeared-out probability map across the sky. The stronger and more structured our magnetic maps become, the more this blurry image comes into focus. The key is that the very highest energy cosmic rays are slightly less affected by these deflections. Their immense momentum makes them harder to push off course, so their paths are a little straighter. By focusing on these extreme events, and by cross-referencing their rough directions with catalogs of known cosmic powerhouses like active galactic nuclei or colliding galaxies, we are slowly beginning to pinpoint the engines capable of such staggering feats. The magnetic skeleton has been hiding these cosmic monsters from view, but by learning to read its subtle contours, we are now turning it into the very map that will lead us to them. Erase the magnetic skeleton from the cosmos, and you would not recognize the universe that remains. The first thing to vanish would be the subtle pressure that currently resists the collapse of giant gas clouds. Without that magnetic support, gravity would reign completely unchecked. Every cold, dark nebula would collapse in a frantic, desperate rush, igniting a firestorm of star birth that would blaze across every galaxy. This would not be the slow, steady candle lighting of our own cosmos, but a single, brilliant flash. Galaxies would burn through their entire reservoir of star-forming fuel in a cosmic heartbeat, creating a population of massive, short-lived stars. These stars would live fast and die violent deaths, exploding as supernova in a relentless, galaxy-wide bombardment. The resulting galactic winds would be catastrophic. With no magnetic fields to channel and suppress them, these outflows would blast into intergalactic space with unimaginable force, completely unimpeded. They would strip galaxies clean of their gas, hurling the heavy elements forged in stellar furnaces, the carbon, oxygen, and iron essential for planets and life, far out into the barren cosmic voids. These precious materials would be lost forever, scattered into an eternal desert, never to coalesce into rocky worlds. The universe would be left littered with starved, aging galaxies, their brief youth spent in a furious explosion of light, now fading into a long, sterile twilight. The cosmic rays, those ultra-fast atomic nuclei, would no longer be trapped. Freed from their magnetic cage, they would race across the universe in straight, deadly lines. A planet forming in this alternate reality would be constantly bathed in this lethal radiation, sterilizing its surface and preventing any complex chemistry from ever taking hold. The great chains of structure we see today would be broken. The magnetic fields that currently guide intergalactic gas along the filaments of the cosmic web would be gone. Without this subtle direction, the flow of raw material into galaxy clusters would be chaotic and inefficient, potentially leading to a more clumpy, disorganized distribution of matter. The universe would lack the elegant architecture we observe, becoming a more formless and haphazard place. Most profoundly, the pathway for life would be severed at its root. The rapid, violent star formation would leave no time for stable, long-lived solar systems to emerge. The constant supernova and the unimpeded cosmic rays would make the interiors of galaxies intolerable. And the very building blocks of planets and organisms would have been violently ejected into the emptiness between galaxies. In this alternate cosmos, there would be no quiet, stable corners, no gradual enrichment, no patient accumulation of the ingredients for life. The universe would be a spectacular but ultimately meaningless fireworks display, a brief flash of frenzied creation followed by an eternal, silent dark. The magnetic skeleton, by holding back this inherent chaos, created the conditions for a long, rich, and structured story. It is the reason we are here to ponder its existence. The invisible cage that has shaped our universe now presents its final mystery. Our journey is far from over. It is simply entering a new and more precise phase. The future of magnetic cosmology hinges on answering three profound questions that have emerged from our exploration. First and foremost, we must find definitive proof of primordial magnetic fields. Did this skeleton truly originate in the universe's first instant, or was it built later? The hunt for the faint magnetic imprint on the cosmic microwave background is our most promising lead, a direct message from the dawn of time that would settle the origin debate once and for all. Next, we must map the full, breathtaking extent of the magnetic web. Current telescopes have given us a sketch, but the Square Kilometre Array will soon provide a high-resolution portrait. We need to understand how these fields connect not just clusters of galaxies, but also the vast, empty voids between them. Is the entire cosmos, even its most desolate regions, threaded with this force? Finally, and perhaps most importantly, we must determine magnetism's ultimate role in the cosmic life cycle. We have seen how it guides star birth and contains galactic winds, but is it a fundamental driver of galactic death and rebirth? Does it play a part in the eventual evaporation of galaxies or the recycling of their material into new cosmic structures? Unlocking these secrets requires a new generation of tools and a deeper theoretical understanding. We are building more sophisticated computer simulations that can model the subtle interplay between magnetic fields, dark matter, and dark energy. We are developing new ways to analyze the light from the first quasars, searching for the unique polarization signatures that only a primordial field could create. The goal is a complete theory of cosmic magnetogenesis, a story that explains not just how the universe built its magnetic skeleton, but why this specific force was necessary for the cosmos we call home. Every question we answer reveals a deeper layer of mystery, pointing toward a reality where the invisible forces are not merely participants, but the very authors of the cosmic story. This invisible architecture now stands at the center of a scientific revolution, its origins fiercely debated. On one side, the primordial theory argues the skeleton was woven into the cosmos at its birth, a fundamental part of the universe's blueprint. The new data from LOFAR, revealing vast magnetic fields in the most empty voids, gives this idea powerful support. How could such extensive fields exist in pristine space unless they were stretched there from the very beginning? The opposing view champions the cosmic battery and the turbulent dynamo, a patient building process where the motions of galaxies and clusters amplified feeble seeds over billions of years. Each theory makes distinct predictions about the strength and structure of the magnetic web, and for the first time, our telescopes are powerful enough to test them. We are no longer just speculating, we are comparing our maps of the sky against simulated universes generated by supercomputers. Every new observation from LOFAR and every fresh data point from the Hubble Space Telescope adds another piece to this cosmic jigsaw puzzle. The tension between these ideas is not a stalemate but a catalyst, driving the entire field toward a more profound synthesis. We are gathering the evidence that will force one theory to evolve and the other to triumph. This is the thrilling precipice we now stand upon. The next decade of observation promises to settle the argument, revealing whether the magnetic skeleton is a relic of creation or a structure that built itself. Either answer will rewrite our understanding of cosmic evolution, finally revealing the true nature of the force that has silently shaped everything from the largest galaxy to the possibility of our own existence. This magnetic skeleton is far more than a cosmic curiosity. It is a fundamental, active component of our universe, an invisible architect that has shaped the very galaxies we call home. From guiding the slow birth of stars to confining the universe's most violent radiation within a labyrinthine cage, this force has imposed a delicate order upon what could have been pure chaos. It paces the growth of galaxies, recycles the elements for life, and may very well be the reason we exist to ponder the stars. By holding back the raw, untamed ferocity of cosmic evolution, it has carved out the stable, quiet corners where complexity can slowly emerge over billions of years. The story of this hidden framework is still being written, its deepest secrets yet to be unlocked by the next generation of telescopes peering into the dark. So the next time you look up at the night sky, remember that you are not just seeing points of light. You are witnessing a universe sculpted by an invisible hand, a grand and beautiful structure whose final chapters are waiting for us to turn the page. Stay curious, for the greatest revelations are still to come.